Thank you so much, Jacob. Thank you so much for this invitation and for giving me the chance of presenting here some historical philosophical reflections on naturalness and the hierarchy problem, which I will try to convince you were and still can be a very useful argument for all seasons as flexible heuristic tools in high energy physics. I will start my talk with a few remarks about naturalness and the hierarchy problem today, stating my thesis, and then I will support it by offering a necessarily sketchy overview of historical developments of notions of naturalness and hierarchy problem from the early days of renormalization as tool and subject of research until more or less today. Naturalness and hierarchy problem today are arguments to argue for the existence of a physics beyond the standard model at high energies. They are usually seen as non-compelling arguments. Sometimes they are described as aesthetic or philosophical arguments. And one thing that one notices when reading the literature is that there are a lot of different formulations of naturalness and hierarchy problem and of their mutual relationships. I am not going to give any overview on them, just quote a couple of examples. I'm sure you know many more. For example, it's often argued that there is an unnatural hierarchy between the scale of electroweak symmetry breaking and the Planck scale, where allegedly quantum gravity should manifest itself. Or often people speak of an unnatural fine-tuning of the standard model parameters, which is necessary to fit observation. These are problems which can be solved by a new physics. Now, what interests me is what is the attitude of physicists towards this variety? It's interesting if you look at the literature from the 1980s onward, when these arguments started being more and more central for high energy physics, you see that in the beginning, physicists hardly ever questioned this variety. They used whatever notion of naturalness or the hierarchy problem was good for their aim, but they did not bother that there were many other notions of them running around. This changed somehow around 2012, and this change, at least a factor in this change was that the Large Hadron Collider at CERN delivered the results of its first run. And in these results, there was no hint of a new physics. And one can see that at that point, especially theoretical physicists started discussing whether these arguments for the existence of new physics should be reevaluated. Perhaps one should try to find which was the correct formulation. The validity was questioned, but the discussion, as you probably know, were more about finding a right formulation of them. And of course, philosophers of science contributed to these debates. Now, my thesis is that indeed the variety, the vagueness of naturalness and the hierarchy problem should not be seen, not even today, as a problem. Actually, it's an asset because it allowed them to be productive, flexible heuristic tools for the development of both theoretical and experimental high energy physics for more than 30 years, and they can still be productive, in my opinion. And I will try to convince you of this claim by going back in time. And since this workshop is also devoted to renormalization, I thought that it would be interesting to look a bit more in detail in the early period of renormalization, when it was used as a tool, but it was also a subject of research, because it was in this context that early notions of naturalness and hierarchy problems started emerging, notions which were quite different from what we know today, but are still quite interesting from a historical philosophical point of view. Renormalization, of course, emerged in the context of quantum electrodynamics, which, as you know, is a theory which combines quantum theory and electromagnetism. The first attempts to formulate such a theory were made already in the 1920s, and already at that time, it became clear that there was a problem, not so much in formulating the theory, but rather in computing with it, because very often when trying to do computation with quantum electrodynamics, authors would come up with divergent expressions, integrals which do not converge. And of course, this is a big problem for a theoretical physicist. And it was only in the years after the Second World War that not really a solution, but at least a workaround to this problem was found. I leave out the very interesting historical details of the story. For us, it's important that from that time onward, a method called renormalization became established to formally subtract divergent terms from these expressions. And what is more interesting, the final finite results were empirically successful. This was at the time quite surprising, in a way still today surprising, given that the theory is still today quite non-rigorous in mathematical terms, but this was the beginning of quantum electrodynamics as we know it today, of which renormalization is a core element. And since I will be speaking of the implications of renormalization for our theme, I thought it might be good to give a very, very rough historical sketch of what happens in renormalization and exactly what is interesting for our topic. I excuse myself with those of you listening who know much more about this topic. Now we have a theory, quantum electrodynamics, or quantum field theory in general. This is, as usual in physics, a formula which contains some symbols representing the masses and charges of particles we are interested in. These masses and charges today are called bare masses and charges for reasons which we'll presently see. And from this theory, one can derive formally some predictions for a given phenomenon, for example, a scattering amplitude with some specific particles. As I said, the problem is that usually some divergent expression come up, integrals which do not converge, or one can even think of expressions like 1 divided by 0, which look mathematical but are not in fact mathematical, they're just not defined. Usually one would have to stop when arriving at such expressions, but that is not what happens in renormalization. There is a procedure to be followed. And the first step in this procedure is to modify the divergent expressions in a way as to make them finite. For example, inserting a cutoff in the integrals, integrating not until infinity, but until a very high value of, for example, n. And here it's important to note that I simplify a bit, but for dimensional constraints, it is necessary to introduce in this step an arbitrary energy scale called E. This will be important in the following. Now, once you have modified the expression, what you do in the next step is to subtract from the prediction formula some terms which contain both the modified expression and these bare masses and charges. You subtract, you take those pieces out and instead instead of them new terms which are finite and contain the measured values of the masses and charges, which take the name usually of Dresser constants. Having done this, you obtain a finite numerical prediction for the phenomenon, which, as far as we were able to check, works. And here it must be noted that this arbitrary energy scale, which had been introduced, is still there. Somehow it can be moved around formally, but it's still there. However, all observable quantities are fully independent from it, which is a good thing. However, other expressions are not necessarily independent from this arbitrary energy scale. Now, this was a historical sketch. Now let's go back to history. From the 1950s onward, theoretical physicists, of course, used renormalization as a tool to compute predictions for observable phenomena, but some of them also explored renormalization to understand better the formal and possibly also the physical implications of these procedures. And these implications were slowly discovered and explored. And if you know something about it today, these are extremely complex subjects, and it took some time for the authors to arrive there. And of course, it also is important to know that at least in the early period, there was an expectation that a mathematically rigorous version of renormalization would be found, but this was not the case. The implication of renormalization became particularly important from the early 1970s onward, because until then, there had been essentially only quantum electrodynamics as a renormalizable theory. But then in the 70s, it was proven that also so-called non-abelian gauge theories, like the Weinberg-Salam model of electroweak interaction or quantum chromodynamics, are renormalizable, and there the implications are even more complex. One point which was let's say, discovered, noted in the early 70s was that in the Weinberg-Salam model, because of spontaneous symmetry breaking, some relationship between the masses and also the charges of the particle are there at zeroth order, which never require renormalization. That is, when computing these relationships, you never encounter divergences. These relationships were noted at the time, and they were often described as natural. This was done by various authors in passing by. Two authors pointed out this issue with particular interest, Howard Georgi and Abraham Pais, in a paper which had the title Calculability and Naturalness in Gauge Theories. Indeed, I think this is the first paper in high energy physics which has the term naturalness in its title. And in this paper, Georgi and Pais wrote that in a theory with spontaneous symmetry breaking, there will be zeroth order relationship between masses and coupling constant, the corrections of which are finite. We will call such relations natural. This property of naturalness, as described here, was of course a formal property. However, Georgi and Pais and also other authors were convinced that this formal property somehow pointed to some special physical significance. What significance was unclear, but authors tried at the time to build theories which contain such natural relationships. And here you see already how this principle of naturalness, which they had at the time, served as a heuristic tool to guide and to motivate, in this case, theoretical research. Now, even more important was, at the time, the reflections on the consequences of renormalization regarding the so-called running coupling constant. As I noted before, renormalization implies the introduction of some arbitrary energy scale E. And in the early 1950s, it was noted that one could formulate renormalization in such a way as to obtain a formal dependence of the renormalized, also dressed masses and charges from this arbitrary energy scale. Observables, of course, remained independent, but you had this formal dependence of, say, electric charge and masses. What was the attitude of theorists at the time? Well, until about 1970s, in general, theories were interested in this issue, but regarded it mainly as a formal one, still a useful one, because you could use it, for example, to simplify some procedures of renormalization, but they did not regard it as particularly relevant in a physical sense, or at least relevant maybe only for very, very high unobservable energies. The first one, or at least the first one with whose work had consequences, the first one to point out that this consideration might have a physical implication, a phenomenological implications, was Kenneth Wilson. His arguments soon were seen as not valid, but he had started something. And a very, very important development came out of it in 1973, as a number of authors, contemporarily but independently, proved that non-abelian gauge theories, for example, quantum chromodynamics, are asymptotically free at high energies. That is, they have a coupling constant which for very high energies tends to zero. Now, this might look again like a very abstract, purely formal property, but actually, as these authors noted, it could be used to explain a rather puzzling observation which had been done already in the 1960s, that is the so-called observation of Biochem scaling in lepton-nucleon scattering. That is, that if you shoot a lepton with a high energy towards a nucleon, it will be scattered as though it was hitting a point-like particle moving freely inside the nucleus. Today we interpret this in terms of quark, but this interpretation was a very important consequence of the discovery of the property of asymptotic freedom. Now, for our story, what is important is the success of this idea, the success in the sense that you could use this formal property to explain observation. This prompted further attempts to find physical interpretations of the running coupling constant. And of course, the development that came from it were attempts to construct a so-called grand unified theory, a theory in which the three known forces, electromagnetic, weak, and strong, are unified, again, at very, very high energies. And the principle is, of course, quite simple. The idea is that at low energy, you have three coupling constants. And if you assume that these coupling constants all change with energy, then, as you can see in this qualitative picture, when the energy rises, one might suspect that the three constants run to the same point at which you have a grand unification and only one coupling constant. Moreover, it was assumed that not only the coupling constant become the same, but also that the three symmetries associated to these three forces become part of a one larger symmetry. Conversely, if you have at high energies one grand unified symmetry, you have to assume that when you go to lower energies, this symmetry is broken. And of course, it was assumed that the symmetry would be spontaneously broken, which was a good idea. The problem was, and still is in a way, that of course, this symmetry breaking had to somehow fit observed phenomena. And this implied that one had to have one symmetry, which was spontaneously broken twice at two quite different energy scales. And building such a theory was not so simple. Indeed, as authors noted in the late 70s, this usually required a lot of fine-tuning in renormalization. And indeed, even with fine-tuning, it was doubtful whether it was possible at all. The problem was that this fine-tuning not only was in itself difficult, but it was also regarded as unnatural. This was, again, a term, unnatural in the sense which we have seen in the previous slides, that came up also in this context. And Eldad Gildener, a theorist who had worked quite a lot on these topics, wrote that a gauge hierarchy was this hierarchy of symmetry breaking of gauge theories. A gauge hierarchy would be compelling only if it occurred naturally. And naturally here meant without fine-tuning, and possibly even naturally in the sense of Georgian pies. One would like to find some relationship which does not need to be renormalized at all. But this was not simple, and this is what at the time was described as the hierarchy problem, or the gauge hierarchy problem, which was of course also a problem of naturalness. So you see, I hope I've shown that starting from reflection on the consequences of renormalization and their physical implication, notions of hierarchy problem and naturalness emerged, which were very useful in driving research, motivating research. Although these notions were quite different from what we have today, soon a turning point would come. And this turning point, as I think is well known, came around 1980, when three very important papers were published by Leonard Susskind, Gerhard Toft, and Martin Weltman. In these papers, each author gave his own new definition of naturalness and used this definition for a very specific aim. I will just shortly sketch them. You probably know these arguments. For me, what is important is to see how the same argument could be tweaked in one or the other direction, redefined to serve a specific aim. First of all, Susskind, the first one to publish, brought forward an argument which is today quite famous, that pointing out that in the renormalization of the Higgs mass, using as a cutoff the Planck mass, relative corrections must be adjusted to the 38th decimal place, and these adjustments are unnatural and will be assumed to be absent in the correct theory. And what is the correct theory? Well, of course, Susskind was there to present the correct theory. His argument was that because of this naturalness problem, the Higgs boson should not be regarded as an elementary particle, but rather as a composite of so far unobserved elementary particles, which interact with, again, so far unobserved new force, which Susskind in this paper called heavy color and later on would be called technicolor. And here it's important to note that the definition of naturalness for Susskind was only the starting point in the first page of the paper to go on and argue for the theory of technicolor. Shortly afterward, Gerhard 't Hooft published also a paper on naturalness. And here he took a very different approach than Susskind. He defined naturalness as a dogma. He used this term. And the dogma was that at any energy scale E, a physical parameter x is allowed to be very small only if the replacement x to 0 would increase the symmetry of the system. Here, for 't Hooft, symmetry played a very important role. But again, the aim of the paper was not to define naturalness, but to use this definition for a specific argument. And in the case of 't Hooft, he argued that technicolor, as defined by Susskind and other authors, was not a natural theory. The third paper was written by Martin Veltman, and Veltman proposed what he called a naturalness criterion, which was, in a sense, a refinement of Susskind's criterion. The criterion was that relative corrections are supposed to be of the same order or much smaller than the actual observed values. And interestingly, Veltman had a criterion of naturalness which was, in a sense, similar to that of Susskind, but he used it to argue in a different direction, namely that not technicolor, but supersymmetry is a natural theory. I'm not going into more details about these works, but I would like just to point out some similarities and difference of the three approaches, again, to see how flexible these naturalness arguments could be. One point which is interesting is that all three authors, in one way or the other, connected naturalness with the problem of matching two very different energy scales. And from this view, a new form of hierarchy problem was born. That is, you see in the following literature, people speak of a hierarchy problem, but not anymore with reference to grand unified theories, but rather with reference to the hierarchy problem sketched by these three authors. But as far as differences are concerned, an interesting point is, for example, that, as I noted, 't Hooft gave particular importance to symmetries in discussions of naturalness. And so in the following years, authors who were interested in symmetries often picked up 't Hooft definition, speaking of naturalness, which requires symmetries protecting small parameters. Then again, another important difference is that both Susskind and Veltman, to define naturalness, had to assume an energy at which new physics was valid. And then once they had that assumption, they could argue that one specific new model was natural or not. That is, they had to assume the existence of new physics to argue for one or the other model. With 't Hooft's definition, on the other hand, one could argue for the existence of new physics at high energies, because one could argue that the standard model at some energy becomes unnatural. So 't Hooft's criterion of naturalness could be used to argue for the existence of new physics. So depending on what you wanted to do, you could choose one or the other direction or create a different one. And that's what happened in the following decades. One thing that happened quite soon in the early 1980s was that a very strong connection was established between the naturalness criterion and supersymmetry, a connection which is very well known today. But as we saw, the naturalness argument was not born to support supersymmetry. However, in the early 1980s, many authors noted how supersymmetry could ensure the absence of the quadratic divergences of the Higgs mass, which were the element which Leonard Susskind had described as unnatural. And therefore, these authors could say that supersymmetry was a particularly natural theory. Moreover, other authors noticed that supersymmetry could help solve the gauge hierarchy problem of grand unified theories, which we have seen before, and which in the meantime had come to be known as the little hierarchy problem, because the big hierarchy problem was linked to the Planck mass. And in this time, you can see really a mutual feedback between supersymmetry and naturalness emerging. That is, authors working on supersymmetry underscored that it was natural, and at the same time pointed out that one had this big naturalness problem or hierarchy problem, which one could solve thanks to supersymmetry. And this is a very well-known mechanism in the history of science, where a problem and its solution are very closely linked to each other. One thing that is also worth noting, in 1984, the so-called first string revolution took place, where it was shown that string theory does not need to be renormalized, and string theory was presented at the time as a natural theory. From the middle of the 80s onward, these arguments of naturalness and hierarchy problem could be used more and more often, also to simply motivate experimental research for new physics beyond the standard model. Although they were born to support one or the other model, they actually could be used also by experimentalists saying, look, we have this problem, there has to be new physics, we have to build a new big experiment. And again, here the flexibility came to the fore. And to give you an example, one can look at the relationship between supersymmetry and naturalness at the lab experiment. The lab experiment at CERN started in 1989 with the first phase with a lower energy, and then from 1995 onward, the second lab phase started with a higher energy. Just before the start of Lab 1, Barbieri and Giudice, two theorists, published a paper giving upper bounds on supersymmetric particle masses. As I think you know, supersymmetry predicts that for each known particle, there has to be a superpartner, which, because of the breakdown of supersymmetry, has a very high mass. Now, Barbieri and Giudice argue that the supersymmetric partner with the lowest mass, for reason of naturalness, had to have a mass a bit lower than 100 GeVs, and therefore would certainly be seen at Lab 1. It would have been, they said, unnatural not to find superpartners at Lab 1. However, in 1995, it became evident that Lab 1 had found no evidence of superpartners, and at that point, two other authors, Anderson and Castagno, published a paper criticizing Barbieri and Giudice and providing a definition of what they called measures of fine-tuning. That is, arguing that, yes, fine-tuning is a natural, but you can measure how much fine-tuning is natural and when it really becomes unnatural. And in this way, they could argue that supersymmetry could be natural despite the negative results of Lab 1. Therefore, naturalness, thanks to its flexibility, lives on. And here, I would like to say, of course, philosophers might say, well, but this is an ad hoc argument. You can just turn it any way you want. It's not really productive. But actually, a heuristically productive argument, in my opinion, is an argument which helps get new ideas, come to new ideas for theories or for experiments. And in the history of science, very often when you make a discovery, you discover something that you were not really looking for. So if you have an argument which is flexible and brings people to new idea, this is heuristically productive. And in this sense, one can see that hierarchy problems and the natural principle could also be linked to, used to interpret or at least applied to experimental situations. For example, in 1995, when the top quark was discovered at Tevatron, it was noted that the top quark has a mass much higher than that of the other quarks. And this situation was described as unnatural. Why unnatural? Because you have, again, a hierarchy problem, two very different masses within the standard model, and the standard model does not provide any kind of explanation for this. You just have to plug in these mass values. In a similar way, when it was discovered that neutrinos have a very small but non-zero mass, this was described as unnatural, because just in the same way, something which is so small but not zero This has to be maybe protected by some symmetry, which is, however, not there in the standard model. Again, in this case, an experimental result could prompt reflection thanks to argument of naturalness or hierarchy. From say around the turn of the millennium, in expectation of the start of the Large Hadron Collider at CERN, one can see that the situation becomes even more complex. A real new generation of proposals for new physics appear. These are proposals which all claim in some way or another to solve problems of naturalness or hierarchy, but they very often give new twists to these notions of naturalness or hierarchy, and it would be impossible to give here an overview of these developments. I personally have no overview on them, but I would like in the last maybe 5 minutes or so recall the one model which made a new and in fact quite original proposal for solving the hierarchy problem. And this is a model which is also, I think, quite well known, though I think it's not regarded anymore as very actual today. This is one of the many so-called extra-dimensional models proposed from 2000 onward, which employed methods from string theory to build models to be tested at LHC. And it is the so-called ADD model from the names of the theorists proposing it, or also the large extra-dimensional model. The hierarchy problem appears already in the title of the paper in which the model is proposed, the hierarchy problem and new dimensions at a millimeter. And I would like just to read to you or with you the beginning of the paper, because they really put the hierarchy problem at the start. They propose a new framework for solving the hierarchy problem, which does not rely on either supersymmetry or technicolor, the old solutions. In this framework, the gravitational engaged interactions become united at the Wick scale. That is the scale of electroweak symmetry breaking, which we take as the only fundamental short distance scale in nature. The observed weakness of gravity on distances larger or equal to 1 millimeter is due to the existence of 2 or more new complex spatial dimensions, large compared to the Wick scale. So the Planck scale, which is of course very large, is not a fundamental scale. Its enormity is simply a consequence of the large size of the new dimensions. That is, the hierarchy problem in the sense of the big difference between the electroweak and the Planck scale is now solved with a very radical move, lowering the gravity scale, claiming that the Planck scale is just a byproduct and the real scale of gravity is the electroweak scale. And the interesting thing in this paper, in this model, is that in its original form, it implied or postulated a deviation from the classical gravity formula from Newtonian gravity at short distances, short but still observable. In the original form, as I said, something like less or equal to 0.1 millimeters. And you can see this in this image, which is from a paper by Murata and Tanaka from Classical and Quantum Gravity in 2015. There you see the red line, which is the coupling constant to the strength of gravity, which follows the Newtonian line, but then according to the model, at some point deviates to go and join the coupling constant, the strengths of electroweak forces. And as you can see from the picture, you can test whether this model is correct or not through collider experiments, of course, but you can also test it by laboratory experiments, looking at searching for possible deviation from Newtonian gravity as short distances. And the interesting thing is that when this paper was published, physicists started looking at what kind of experimental proofs, experimental tests of gravity at very small distances existed. And there were some, but not so many, because nobody had really cared very much about this test until then. And so also new laboratory tests were done, precision tests. And well, of course, no deviations were observed. So the model had to be, again, modified. But this is not a problem. What I would like to underscore in this example is how the hierarchy problem with this new twist could even motivate research outside of high energy physics. And again, I think the heuristic power is something like this, just having people get new ideas and search where nobody would have thought to search before, and maybe you find something. And with this, I have arrived at my conclusion, which are not very much, let's say. Going back to the discussions that have started since about 10 years of whether one should sharpen, redefine, or perhaps even abandon the principle of naturalness or the hierarchy problem. Well, in my opinion, none of the above. I think the variety and the vagueness of the natural principle and the hierarchy problem should not be regarded as weaknesses, but rather as a strength, because both principles, because of this, could be flexible and productive heuristic tools for high energy physics for more than 30 years, and not only for theory, but also for experiment. And perhaps they may provide heuristic guidelines also for future research, maybe if one does not take them too seriously, but just as a heuristic help to motivate research and come up with new ideas. Thank you so much for your attention.
Thanks so much, Arianna. That was a wonderful, wonderful talk.
Thank you so much. Should I stop sharing yet?
No, please keep the screen sharing up in case people have questions about any of your slides. If that's all right, if it's all right with you. All right, so we have a few minutes for questions. I have a couple, but I tend to prefer to give other people an opportunity to ask first. So if you have a couple of questions, please use the hand raising tool. If you'd like, you can also put your questions in the chat. If you'd like to ask a question anonymously, I would encourage you to ask a question not anonymously, but if you'd like to ask an anonymous question, you can send a question directly to me using the chat tool, and I will read it without saying your name. Great, I see a question from Josh. Josh, go ahead.
Thanks very much, Arianna. That was great. I guess I wanted to ask you, so the approach seems to be sort of a let many flowers bloom sort of attitude towards naturalness. And of course, we know that that sort of attitude can go too far in a way, right? Mm-hmm. So you have to make decisions about what to research, and you have to whittle down the options. And so I'm just wondering, how this kind of falls short of that in a sense. Because we can't be completely democratic, I guess, in the ideas that we pursue. So what's the restriction here, right? Why is this, what is the principle that kind of that helps us whittle down the sort of, likely avenues for research?
Well, as I said, from a historical point of view, it's difficult to talk about principles. One thing that I would say, because I totally agree with your remark that you have to draw some line somewhere. Perhaps what I said before, that one should not take naturalness too seriously. Would be a point. I think it's good to try this, try that. Of course, if you get stuck with one definition of naturalness and you again and again don't come up with new ideas, then you start to have a problem. Maybe I would say just like this: if at some point you see that you're stuck, you really don't have any more ideas, then you could try to maybe find a new definition of naturalness. I don't think that, or some new name. I think that in a way, as I argue together with Elena Castellani in our paper, you can see similarities between naturalness and other criteria that were there in the past and that were used, but also not taken too seriously. But the problem is always there, what you say, and it's really a problem.
Yeah, thanks. I really enjoyed that paper, by the way.
Thanks, Josh. The next hand I have is Sebastian. Sebastian, go ahead. And Josh, if you're done with your question, if you would lower your hand. Thanks.
Thanks, Arianna. Yeah, it was like a very nice and interesting talk. I've got a quick comment and a quick question, which is related to Josh Vasquez's question, I guess. the quick comment is about Wilson understanding of like running couplings. I think he already gives like a physical interpretation of like couplings earlier, like in 1965. And of course, like in the 1970s, the early 1970s, it becomes like a bit more clear in his mind, I guess. And then the quick question is, so basically like in the 50s, in the 60s, and I guess even the 70s, people were using many kinds of arguments, but like a model or like a theory being unnatural or not. And the best example is when the model was involving like too many parameters, for instance, like it was deemed unnatural. And of course, I can just take that to be a purely aesthetic remark, even not even an argument on like the features of the model. And so I was wondering if you had found like in your historical research ways of like distinguishing between like purely aesthetic and vague naturalness arguments and more heuristically productive ones, because it seems that in the standard naturalness problem in energy physics, it is indeed very productive, but people have been using many similar or vaguely related arguments, which were definitely not very productive. I mean, if you just say, oh, my model has too many parameters, then you try to reduce the number, it's not going to give you many hints as to where you should go. So that's my question. Like, have you detected specific ways in which like naturalness arguments were actually becoming more and more productive in those years?
Well, thanks. This is a very good question. And let's say from a historical point of view, as far as I can see, it's difficult to make this distinction between, okay, what could make a distinction between arguments that were just a study made in passing by and arguments that really drove research a lot. As far as productivity is concerned, this is difficult, and it's difficult because of the context. So if you take people working in the 1970s, where they start talking about this naturalness and renormalization, I would say that there you see a lot of productivity, and also partly in the 80s. The problem is that part of that productivity is also due to the fact that they're working in at a time where you get new experimental results that can be, for example, let's say with the Biochem scattering, or later on with the observation of new quarks. So perhaps also with regard to what Josh was saying, I think these kind of arguments showed their productivity at best when the problem was matching theory and experiment, because you could get a lot of new ideas of what to connect or not connect. For example, the naturalness argument allowed to connect high energy physics with cosmology, which was a very important and I think also productive step. Perhaps one could say that when they became only internal arguments within, for example, for defining which kind of supersymmetry could or could not be natural, then they are perhaps less productive. But I'm so much of a historian that I'm always hesitating to make this normative judgments. And I also have to say that I have not tried systematically to answer your question historically. It's a very good one, and I will try to do that. Thanks.
Thanks so much. The next hand I have is Alex. And then I also have an anonymous question in chat that I'll ask after Alex.
Thanks for the talk. That was really nice. This is maybe related, I'm not sure. But I was just wondering if, like, what you think of the kind of context of discovery, context of justification distinction, and whether or not that can be kind of usefully applied here. Where I wonder if sometimes people use naturalness arguments in order to kind of justify their theories. This is a better theory than that one, or this is the right theory because it's natural, rather than I took much of your arguments to be involving this is a really useful heuristic for discovering new theories, and then we can come to the justification thing later.
Well, First of all, now I realize maybe I should say I've tried to break a lens for naturalness because it's been so criticized. So this is not, I'm not trying to be really an advocate for it. However, on your question on the context of discovery and justification, well, let's say as a historian, of course, historically, this is a very important distinction, how people argue when they are trying to discover something and how they argue a posteriori when they're trying to explain what they have found and why that is good. I think that, but yet I think that from the point of view of the heuristics, it's difficult to make this distinction because to say that there is something there is a criterion which is only useful in the context of discovery and not in that of justification. There, I think this is not the case. I don't think that from that normative point of view, you can distinguish them. I think that's a problem. Of course, if you look at what people are saying, yes, it may be a little bit of a problem when trying to use too much in the justification this criteria. But I think from the point of view of the heuristic, it's difficult to make the distinction. I don't know if I answered your question. Please.
No, that was very helpful. Thank you.
Great, thanks, Alex. So I have an anonymous question in chat. The question is, what do you think of the unnatural solutions to some simple puzzles, like Archimedes' cattle problem, which is simple, but the solution is of order 10 to the 200,000, or the smallest counterexample of Euler, in which he says that there are no solutions of the equation a to the fourth plus b to the fourth plus c to the fourth equals d to the fourth in integers, but the smallest counterexample comes in the 100,000s. These seemingly unnatural solutions to very simple problems suggest that naturalness is not a very good assumption for physical laws as well.
Mm-hmm. So, yes, well, I have to say this is, first of all, I was not trying to argue that naturalness is very, very good as a solution. Perhaps if in the spirit of which I hope the question was asked, I could say, well, the fact that you have a very simple question and a very complex answer it's in a sense it's heuristically interesting, this surprise, because it prompts you to look, but where does this complexity come from? And maybe you learn something of the complexity of this apparently simple problem. So one could, but this is just hypothetical. So, but I don't think that there is any kind of rule where that naturalness is always useful or to establish where it is useful. Yeah, it's just something that might be useful. And I don't know if I answer the question in a good way. Unfortunately, as it is now, I can't see. Maybe I can't see the chat. No.
It was a private message.
Okay.
Yeah. So we have a couple more minutes. I'm hoping I could ask maybe one question now. I've got some more questions that I'll save for the discussion period after the three talks that may also be better to ask once everybody has had a chance to speak. But I guess, given the historical focus of your talk and your argument that naturalness has been very fruitful in terms of suggesting directions for research, for theoretical and experimental investigation, I guess maybe then it's just to play devil's advocate here. It might be worth asking, what does the track record look like? These arguments, naturalist arguments, have been around for, at this point, 50 years, something of order like 50 years. And they've, suggested many possible research directions. As you noted, Technicolor, one argument for Technicolor was that it answered a certain kind of naturalist criterion, obviously supersymmetry, extra-dimensional models, guts, grand unified theories, axions as a solution to the fine-tuning problem that's the strong CP problem of QCD. I think maybe it might be worth asking, none of these have borne out. We haven't found axions, we haven't found supersymmetry or Technicolor. Grand unified theories are experimentally disfavored at this point. these naturalist arguments may have generated a lot of research directions, but is it possible to generate a lot of research directions and discover that maybe those directions in the end weren't the best use of everyone's time? This isn't maybe my views personally, but I do know that this is definitely an attitude that some people have about naturalist problems. So is it good to generate research directions that ultimately don't bear fruit?
Well, again, this is a very normative question. Yeah, is it good or bad? No, well, one thing is, of course, you may have to wait to see if things bear fruits or not as a historian. But of course, I'm not trying to say that all of these things will bear fruit. Of course, this is a problem, and yes, at some point one has to change. One has to throw away naturalness or redefine it. As I said, the good thing which I try to underscore in this natural issue is that there is no definition. You could turn it however you wanted. I think what is problematic, and this is, I don't know if it's linked to your question very much, but this is something where I would dare to be normative, is that if you have some definition of naturalness, let's say, and then you do some research and you find something which is actually productive, it's actually correct. Yeah, this does not mean that the notion of naturalness you started from is correct. Yeah, maybe you found it helped you there, but this does not mean that criterion is going to help you further. This is something which is there one should be wary. Yeah, that to think that if you found something that this is a proof that the naturalness, that actually reality has to be natural. So I think it goes both ways. So if it's a criterion that brought you nowhere, well, yeah, you cannot say that it was wrong, it just was not productive. But on the other hand, if it's productive, it's not necessarily good. I don't know if that in some way links to your question.
No, that's great. Thank you very much. That's great. All right, so we have about 5 minutes until our next speaker. That's going to be Alex. So why don't we take a 5-minute break? But Alex, about 2 minutes before the hour, if you could share your slides. And Arianna, thank you again for an amazing talk. And I want to thank Arianna again for a wonderful talk. Arianna, if you would unshare your slides, and I'll stop the recording now.